Now we're going to look at taking the limit of a function. So consider this function. F of x is equal to x squared minus 1 divided by x minus 1. If we plot it out, it looks something like this. A straight line crossing the y-axis at y equals 1. But if you look at that formula, if I let x equal to 1, f of 1 equals 1 squared minus 1 divided by 1 minus 1, which is equal to 1 divided by 0, which is undefined. You cannot divide by 0. So this function is undefined at x equal to 1. So the domain must be the real numbers except for 1, because it's undefined there. But if I look at some points close to this undefined point, the function seems well behaved. I can pick some x values really close, getting closer and closer to 1, and I can work out what the y values are. And we can see as x gets closer and closer to 1, y seems to get closer and closer to 2. And of course at x equals 1 I've left the box blank because it's undefined there. In fact, we can make f of x as close to 2 as we like by making x sufficiently close to 1. In this case, we say that the limit of our function x squared minus 1 over x minus 1, as x approaches 1, is equal to 2. So those statements are essentially equivalent. If the limit of that function as x approaches 1 equals 2, it means I can make the function as close to 2 as I like by making x sufficiently close to 1. If we leave out the point where x equals 1, say x is not equal to 1, then we can rearrange this expression and see that we get the limit of 2. So x squared minus 1 divided by x minus 1 is equal to x plus 1 times x minus 1 divided by x minus 1. I get that from the general principle that x squared minus y squared for any x and y is equal to x plus y times x minus y, the difference of two squares. And if you multiply out there x plus 1 times x minus 1, you'll get x squared minus 1. So now, if we know that x is not equal to 1, or we're leaving that point out, we can actually divide on the top and bottom of this equation by x minus 1. So we basically cancel these two terms with each other, and we just get x plus 1. So if we leave out that point x equal to 1, we find that this expression, or this function, is just equal to x plus 1. And now it's easy to get the limit. So this is the same as the limit as x approaches 1 of x plus 1. And this limit can easily be found by substitution. So if I just put in x equal to 1 in that formula, I can get the limit. So that's equal to 1 plus 1 is equal to 2. Some limits are easy to find. For example, if I want the limit of 2x plus 3 as x approaches 2, I can just plug in 2 there. That's equal to 2 times 2 plus 3 is equal to 4 plus 3 is equal to 7. If I can get a limit by just plugging in the number like that, that's called finding the limit by direct substitution. Here's another example. The limit as x approaches 2 of x squared plus 5x minus 14 over x squared minus 5x plus 6. So the first thing we'll try is substitution. So if we put in 2 there for x, we get 2 squared plus 5 times 2 minus 14 divided by 2 squared minus 5 times 2 plus 6. That gives us 4 plus 10 minus 14 divided by 4 minus 10 plus 6, which gives us 0 divided by 0. So this is no good. Direct substitution won't work here. So what I will have to do is rearrange this expression in such a way that I can find the limit. And what I will do is, like the last example, I'll factorize the terms I have on top and bottom of my fraction, and then I'll see if I can cancel something. So let's write this down. X squared plus 5x minus 14. X squared minus 5x plus 6. So this is equal to, I'm going to factorize the top and I'm going to factorize the bottom. So in both cases I'm going to have x plus something on both sides. Now on the top, the two numbers that I put in will have to multiply together to make minus 14, and they'll have to add together to make plus 5. So what I need is plus 7 and minus 2. So if I multiply out x plus 7 times x minus 2, I'll get back my x squared plus 5x minus 14. And the same on the bottom. I need two numbers that multiply together to make plus 6 and add together to make minus 5. And those two numbers are minus 3 and minus 2. So if I multiply that out, I'll get back my x squared minus 5x plus 6. And in fact, I would have expected that x minus 2 would be a factor in both of these things, since I already know that they both go to 0 when x is equal to 2, because I already worked that out. So looking at this, if I ignore the point where x is equal to 2, because I'm only looking for a limit as we approach that point, then I can cancel these two terms. Divide top and bottom by x minus 2. And so I'm left then with just x plus 7 divided by x minus 3. So now I've simplified my limit, since I know that if I leave out x is equal to 2, now I just need to find the limit of x plus 7 divided by x minus 3 as x approaches 2. And this one I can do by substitution. So that's equal to 2 plus 7 divided by 2 minus 3 is equal to 9 divided by minus 1 is equal to minus 9. Now we look at the limit as x tends to infinity. So consider the following function. F of x is equal to 1 over x. Now, as I make x larger, 1 over x is going to get smaller. If I make out a table of x and f of x is equal to 1 over x, if x is equal to 1, then f of x is 1. If x is 10, f of x is 0.1. If x is 100, f of x is 0.01. If x is 1000, f of x is 0.001. And in fact, we find that we can make f of x as close to 0 as we like by making x big enough. So what we would say is that as x goes to infinity, 1 over x goes to 0. So we'd write that as the limit as x tends to infinity of 1 over x is equal to 0. So that statement means that I can make 1 over x as small as I like, or as close to 0 as I like, by making x sufficiently large. Here's another example. Let's say f of x is equal to 2x minus 1 divided by x. What is the limit as x tends to infinity of that function? Clearly, when it comes to infinity, we can't do direct substitution, because this thing then just looks like infinity over infinity. So let's take a few values and see how it looks. F of 1 is equal to 2 minus 1 over 1 is equal to 1. And let's take some big values. F of 100, it turns out to be 1.99. F of 1000 is 1.999. F of 10,000 is 1.9999. So a picture is emerging here. It looks like our limit is going to be 2, as x approaches infinity. And in fact, we can make f of x as close to 2 as we like by making x sufficiently large. The way that we would work this out is by dividing top and bottom by x in this expression. So I'd say that my limit of f of x, right, is equal to the limit as x approaches infinity of 2x divided by x minus 1 divided by x over x divided by x. So I've divided there top and bottom by x. And if I work that out, that's the limit as x approaches infinity of 2 minus 1 over x divided by 1. And now I know what the limit of 1 over x is as x goes to infinity. So that is equal to 2 minus 0 over 1 is equal to 2, which is what we expected. So the limit of 2x minus 1 over x as x tends to infinity is 2, which means that I can make f of x as close to 2 as I like by making x sufficiently large. Here's another example. The limit as x approaches infinity of 3x plus 1 divided by x squared minus 4. So the first thing I'll do is divide by the biggest power of x that I can see. So that's going to be 3x divided by x squared plus 1 divided by x squared divided by x squared minus 4 divided by x squared. So that's equal to the limit as x tends to infinity of 3 divided by x plus 1 over x squared divided by 1 minus 4 divided by x squared. Now I said before that the limit of 1 over x as x tends to infinity is 0. But this is also true of 3 over x, or any number over x, because I can make it as close to 0 as I like by making x big enough. So that's equal to 3 over x tends to 0, 1 over x squared tends to 0, for the same reason that 1 over x does. 1 is just 1. 4 over x squared also tends to 0. So I get 0 divided by 1, which is 0. Let's consider a different function. Let's say f of x is equal to 1 for x greater than or equal to 0, and f of x equals 0 for x less than 0. So if we plot that, here's x, here's, let's say, y equals f of x. So if I plot it in red, from x equal to 0, so it's 1 here, and it's 1 everywhere bigger, and for x less than that, it's 0. So the function looks like that. So there's a big jump there at x equal to 0. So the question is, what is the limit of that function as x tends to 0? And the answer is, it depends on which side you approach it from. So if I approach 0 from the left, I'm going to call that 0 minus. So this is from the left. That is going to be equal to 0, because I can make f of x be as close to 0 as I like on the left there. In fact, it's always exactly equal to 0. But from the right, what I might call the limit x approaches 0 plus, that limit from the right is equal to 1, because the function is always equal to 1. So this limit actually depends on which direction I approach the point from. There's two limits I can take, from the left or from the right. And here they give me two different answers. So in this case, I would say that the limit here, without specifying left or right, the limit as x tends to 0 does not exist. The limit only exists if the limits from the left and from the right give you the same answer. The reason that limit does not exist as x tends to 0 is because at x equal to 0 there's a sudden jump, or what you'd call a discontinuity, which brings us on to the idea of a continuous function. Intuitively, we might say that a function is continuous if there's no jumps in its graph. So for example, this function in red would be continuous, whereas this function in blue with a jump here would be discontinuous, and that jump would be called a discontinuity. For a function like that red one, we can take the limit everywhere, and it's going to be equal to the value of that function. For the blue curve, we're not going to be able to take the limit right at that point. Let's call it x0. One way to define continuity mathematically is to say that a function is continuous at a particular point if it's equal to its own limit as x approaches that point. So here, we say that a function f of x is continuous at the point x0 if and only if the limit of f of x as x tends to x0 is equal to f of x0. So you can see that at the discontinuity, the limit just doesn't exist. So one way that you could define continuity mathematically is to say that the function is continuous at a point if it's equal to its own limit at that point.